So last time we were obviously talking about kinetics. We talked about the rate law and sort of how you sort of solve for the rate law. Remember, the rate law is a little bit different than sort of the rate expression that we were talking about. And that's because it really only takes into account when we deal with the rate law, the reactants. So the reactants are sort of the most important thing here in terms of the rate of the reaction. So the actual rate law actually only takes that into account. We get something like the rate is equal to K times concentration of one reactant to a particular order, times concentration of another reactant to also a particular order. Remember that the orders are sort of like the proportion, if you will, that is needed for those reactants to sort of come together in order to sort of make a specific rate. Um, and sort of depending on the orders, one reactant may be a little bit more responsible for the overall reaction rate than, say, the other. So we looked at a couple of just made up sort of numbers where, if this order was second order for one reactant and first for the other, by changing the concentration of the reactant that is second order, you could actually increase the reaction by, say, whatever it was, I forget, eightfold or something like that. So again, these orders are sort of the proportion of how these reactants need to come together to really sort of maintain a specific rate. Now, one important thing about the orders is that, and the rate law is that it's always found experimentally, which means typically in these type of problems, we're given tables much like the one we're looking at here, and we saw in a previous example, one where you have basically concentrations of your reactants. You also have the initial rates. And what we want to do is sort of figure out how is the rate changing versus the concentration of each reactant. And again, we could do that by doing sort of a rate two over rate one type of calculation and figuring out the orders of each of those sort of reactants. Once we figure out the orders of the reactants, we could add them together, and that will give us the overall order for the particular reaction. Is it first order, second order, whatever it may be, zero, third order type of reaction? We also then can use the orders and the completed rate law to actually find the value of the rate constant. And we could do that by taking any entry from the table and basically plugging it into our rate law and solving for K. Um, any questions on that stuff that we talked about last time? Also important to note is, since we've kind of did equilibrium up front, some schools do kinetics and then equilibrium. Since we've done equilibrium up front, a reminder that the orders are not the coefficients in the balance equation. So they may be the same number or end up being the same number, or they may be a different number. But unlike sort of equilibrium where we go to the equation and basically take that coefficient, here we don't do that. Here we do want to make sure that we use the actual data that's given to us. Any questions on any of that there? All right, so I think if I'm not mistaken, this is where we laid up in terms of the example. So why don't you take a couple minutes here, and what we're looking for is the completed rate law. We also want the value of the rate constant based off of that. So take a couple minutes here and see what you come up with based on this information. Most people kind of take a mathematical sort of approach to sort of solving this. So if you do that, and not change the slide, I suppose. If you do that, what you're looking for, right, is we're basically going to kind of do this rate two over rate one type of guy like we talked about last time, a to the x and b to the y. So if we write just the sort of generic rate law here without the sort of orders figured out yet, it would be K times concentration of our reactants S2O8 2 minus to the X and I minus here to the Y. So what we're looking for when we go there, as we talked about last time, it's not necessarily take the first and second one, but we're looking for two entries in the table where really one concentration remains constant and the other one varies. Again, that's going to allow you to have only really one unknown. So if we look here, we could see here in 1 and 2, the concentration here of our S2O8 remains constant while our other guy here varies. So we're going to start perhaps with experiments 1 and 2, and we're just going to basically put into this guy all the information. As I also mentioned last time, again, if you oftentimes pick kind of the larger rate and put it up on top, you end up with maybe a little bit nicer whole type numbers. You don't have to do that, but sometimes it just helps make it a little bit easier to see everything instead of decimal numbers. So what I'm going to do is basically put everything up from experiment 1 up on top. Put in my numbers here. And now I'm going to come back and put everything from experiment 2 on the bottom. So now we could do a little bit of math here. Again, this is going to be 2. We don't know what k is at this point, but we do know it's a constant, so it's going to be the same. We don't know what x is at this point, but we do know it's going to be the same on top and bottom, which means they will cancel as well. We do a little math here. It gives us, I believe, 2 to the y. Again, as we talked about, this one you obviously could pretty much figure out right looking at it, but you can also do the natural log of both sides and divide it, and that will kind of get you your answer. But in this case, y is going to equal 1 in this particular case. Any questions on that calculation so far? At this point, we then want to kind of return to the table, and since we kept the S208 constant in the first time, we want to keep the I minus constant, which looks like it will be 2 and 3 that will do that. Again, keeping these guys constant, varying our S208 concentration. Again, here I'm going to put my larger number up on top for the rate, and that means all my information from number 3 will go up on top. So that's 4.4 times 10 to the minus 4 equals k r 0.16 to the x and r 0.017 to the y. Coming back now, putting all my lower number there, or smaller number, on the bottom, which would be 2, 1.1 times 10 to the minus 4, k 0.08 to the x and 0.017 to the y. Doing our same math here, that's going to give us a 4 on that side. Still, our k's will cancel. This will get us, I believe, 2 to the x. These guys obviously will completely cancel since we also know it's 1 on top and bottom. This then does us x is equal to 2 in this case. And that would be the order with respect to the S208. Any questions on those calculations there? Now that we have our completed rate law, we can put it in our orders, and that would give us that the rate is equal to k times the concentration of S208 minus, and x was 2. Our I minus x was 1. That means that the overall order here for this particular reaction would be 2 plus 1, which would be third order. Again, adding up really our coefficient, our exponents there. Now that we do have the completed rate law, we can solve for k, and k in this case, rearranging the rate law would equal the rate divided by the concentration of S208 minus, again, we do need to square it, times the concentration there of I minus. And as we mentioned before, you really can choose any one of these entries from the table and put it in there. And I'm just going to go with the first entry, which gives me a K that is equal to 2.2 times 10 to the minus 4 molar seconds up on top. We got our S208 concentration there in our first guy, 0.08. We are going to square it. And we got our 0.034 for our next guy. Doing all that good stuff there, we end up with a number. Let's see. Call it 1.01. Now, what are our units here? Well, 1 in the molarity is up on top, cancels the 1 on the bottom. We actually end up with 1 over molar squared seconds. Or again, you could write something like 1.01 m to the minus 2, s to the minus 1. So that's another way. Obviously, you could do it. Question on that. So this is a very obviously common way that you can determine, the orders of a reaction, also determine the rate constant for a particular reaction. And the units, as we've been talking about a little bit, of the rate constant does give you an indication of what the overall order of this reaction is. Those are the typical units you would associate with a third order reaction. Molarity squared seconds, 1 over molarity squared seconds. Any questions on any of those steps there? Okay. Then let us try one more here, see what you come up with. So let's take a look and see how we're doing. Same approach here. We start sort of the generic rate law. Our rate is equal to K times our NO2. We'll call that X. And our CO, we'll call that Y. Again, we're going to be looking for a couple of entries where we keep one constant, sort of vary the other. In this case, you do have really a couple of options as to sort of how to do that, but we'll start with perhaps start with here. We have 1 and 2 will keep our CO constant, and we'll vary our NO2. So using those guys there, 1 and 2, we end up with, we're looking at the larger rate on top. So we'll go with number 2 up on top. And that's going to be 0.2 to the X and 0.1 to the Y. Putting our number 1 on the bottom, 0.0021. Okay, and 0.1 and our 0.10 to the Y. All right, so doing a little dividing here, 0.0082 divided by 0.0021. This gets us really 3.9047. We do a little converting out here. Dividing that guy there should get us a 2 to the X. And these guys, again, should really cancel. So it's your choice here. As you can see, not always, obviously, because they're experimental information, do you get pretty numbers, right? Perfect numbers. It really is close to 4, but again, you can take your natural log of both sides if you like. Natural log of 2 brings down the X and divide it out. And if you do that, you end up with natural log of 3.9047. Like 1.3621 divided by our natural log of 2, which is 0.693 is equal to X. And if you do that, you end up with pretty close to what you would expect it to be if you rounded to 4. You end up with like 1.97 is equal to X. And we'll roughly call that 2 in this case. It's pretty close to rounding at that point. It's essentially 2. Any questions on that particular one there? Okay, so at that point, we then can keep the NO2 constant and take us to the other guy. That would look like it would be number 2 and 3 will do that for us, keeping our NO2 constant, again, varying our 2 guys here. So we'll look at 2 and 3, doing larger on top, and they're essentially the same, but we'll go with number 3 up on top. And if we do that, 0.2 to Y, putting our number 2 there on the bottom. And number 2 is keeping this guy constant and this guy varied here. All right, so when we take obviously 0.0083 and divided by 0.0082, it's essentially 1, right? And these guys will cancel, these guys will cancel. That's going to give me 2 to the Y. You may be familiar with if something is to the 0, it will equal 1. So Y in this case would equal 0. Again, if you took the natural log of 1, you get 0. Took the natural log of 1.01, you get pretty close to 0 as well. So again, natural logging both sides would technically give you a 0 on the left, and that's why we end up with a 0 here. Any questions on that? That then means that we now have really our orders here. We would have our completed rate law would look something like the rate is equal to K, and our X was 2 NO2 squared. And really, because our Y is 0, that really makes this 1. So most people would probably leave it out of the rate law. If you did, you would put 0, but technically speaking, that would then make it 1. And again, most people would leave it out. Obviously, our overall order would be 2 plus 0, which would be second order. And once we obviously have our rate law here, we could rearrange it now and solve for K. K would be the rate divided by really the NO2 squared. And that basically gives us, if we put in our numbers here, again, I'm taking it from entry number 1 is where I'm getting the numbers from the table. So I'm just going to go off of this guy. And we will end up with 0.0021 divided by 0.1 squared, going to give us a rate constant. And by the way, this is molarity of 0.21 units. Molarity on the bottom, one of them, and molarity on top will cancel. Leaves us 1 over molar seconds, which is typically what we find for second order, 2 sets of units. Yes. Any questions on any part of that calculation there? Questions on how to determine the rate law or the orders from experimental information? Again, if it's really close like we had there with the 1.97, you can probably round safely in most cases. All right. Okay, then I think we've done enough of that, so we'll skip that example for now. Let's talk about different types of reactions. So we talked about how to determine the orders, determine the overall order of a reaction. Now we're going to talk specifically about sort of individual types of reactions, first order, second order, and zero order reactions. And a couple of things about first order. First off, we've actually, again, have seen first order is pretty much what we use when we dealt with really kinetics in nuclear chemistry. Remember, all radioactive decay basically follows first order kinetics. And basically, there's a couple of ways you can get to first order. You mainly will have usually one reactant that obviously has an order of 1. Other way you could get to it would be 2 reactants where the other guy has an order of 0, right? And obviously would not affect the rate. By the way, that is what we just saw in that last example. What does that really mean when that guy has a 0 order? It means obviously if you did anything you wanted to, just to go back for a second there on that one guy. You know, what does this really mean when this guy, you know, how does that affect sort of the rate of the reaction? Well, if you were looking to maybe increase the reaction or decrease the rate of the reaction, if you decided to play with CO's concentrations, it really would not have an effect on the overall rate, right? Because the order 0 will always end up being 1 in terms of this sort of formula here, which means if you did want to sort of play with a concentration to maybe speed up the reaction, lower the rate of the reaction or something like that, you would in this case have to focus in on the concentration of NO2, as it is obviously the only thing in the rate law that really does sort of affect the overall rate of a reaction. So again, this is sort of the practical applications of what you can do with a rate law or the orders and that type of stuff. You know, again, if you, for example, were doing this experiment that we just did in this example, and, you know, it was happening like way too fast for you, like way too fast for you to be able to measure any type of values and stuff like that. What you would want to do is probably play with the concentration of NO2, maybe lower the concentration or something like that. And then maybe that will allow it to kind of slow down and stuff like that. You wouldn't want to play with the CO's concentration, as again, it would have probably no effect on the overall order of that react or the rate of that reaction. All right, so with that being said, obviously first order reactions, when we rearrange that rate law, we end up with units that are associated with first order, and these are really important. So as I mentioned a number of times, the actual units of the rate constant are really important because it does tell you the overall order of a particular reaction. And a lot of times in kinetic site problems, they don't with flashing lights go, hey, you're doing a first order reaction now. You're doing a first order reaction. Use the first order sort of equations and stuff like that. So they really don't sort of, in a lot of cases, kind of straight out tell you, hey, this is first order, or second order, or zero order. What they will oftentimes do is sort of give you the value of the rate constant, and they'll give you the units that are associated with that rate constant. And they expect you to know that, oh, I see 1/seconds. I am dealing with a first order reaction, which means I really should be using the first order sort of equations and formulas and stuff like that. Now, when we look at this 1/seconds or reciprocal seconds, it doesn't always have to be seconds in terms of the units. It can be really any unit of time. So you could have like 1/minutes, 1/hours, 1/days, weeks, years, whatever it may be. But it's really 1 some unit of time. Although, obviously, if we do some type of experiment, say in the laboratory, we probably aren't going to be running it for days or years or things like that. So seconds is a very common unit that's used. But again, just a side note, it does not necessarily have to be a unit of seconds for it to be first order. You could have something like 1/minutes, which also would indicate that is first order. So it really is that like 1/unit of time that sort of makes it a first order reaction. Now, when we look at a first order reaction, we see two common plots that are oftentimes used in first order. The one on the left is really a plot of concentration versus time. And as we would expect in this reaction, over time, the amount of A should be decreasing, and really the amount of the product should be increasing. And if we plot the concentration of A versus time, we do see that as time goes on, we are decreasing, right, the concentration of A, because really it's getting converted over to products. Now, although this is a nice graph here, this is usually not the one that people associate with sort of first order kinetics. They associate this one over here. And this one is really written in the form of y is equal to mx plus b, the equation for a straight line. And usually in kinetics, that is like the big equation there. That is what we really try to relate data into, kind of how it fits linear to each other in a sort of straight line. And that brings us to really coming across this equation here and doing a little natural log action there and getting what is sometimes referred to as the integrated rate law, or the time concentration dependence sort of equation here. And what does all this mean? Natural log of A is equal to the natural log of A naught minus KT. A you can kind of think of as like your final concentration. A naught is like your initial concentration. K is our rate constant. And also really important at this point is T is time, not temperature. So oftentimes we've seen T all day, all year, and it's all about temperature. But again, that's lowercase t, and that is actually a unit of time. If we take that formula and sort of rearrange it a little bit and write it as the natural log of A is equal to minus KT plus the natural log of A naught, that is the first order integrated rate law written in the form of a straight line. That is y is equal to mx plus b. That means if you look at our graph over there on the bottom right, on the y, natural log of a, on the x there is t. And obviously in this case, as you can see from here, our slope would actually equal not k, but actually negative k. Why is that? Well, the slope of this line is negative, right? It's a negative sloping line, which means your slope will be negative, and negative k will turn your rate constant into a positive number. Yeah. So that negative basically will turn that into a positive number. So that is definitely a graph that we very commonly see. We'll actually see this graph here in just a bit for another order reaction, but the graph on the right is really the one that we associate with a first order plot. There's also the, as we will see, and I'll just jump the gun here a little bit, there's a half-life equation, which is the natural log of 2 divided by the rate constant, and that's basically 0.693 divided by K. And the half-life equation and the integrated rate law, you sometimes have to use together, as we saw, I think, in nuclear chemistry a number of times, to find something like the rate constant or something like that. So these are, again, specific for first order. Any questions on that there? So what do you really need to know? Well, you need to know that the K has these units are typically associated with the first order. You definitely need to know the integrated rate law here. And you do need to know, obviously, the half-life equation. And you do need to know that this graph here is the one that is associated with a first order plot. Any questions on that there? Here again is another first order plot. If we took the slope of that line, which is the change in the rise over run, it would equal minus K for this reaction. And again, you can see a pretty linear relationship that occurs, and that is very common why we kind of do these sort of linear graphs of these guys. All right, so why don't you take a second here and let's try to figure this out. If we have a reaction that's first order with A, it has a rate constant of 2.8 times 10 to the minus 2, how long will it take for A to decrease from 0.88 to 0.14 molar? Okay, so let's take a look. So we obviously are given K in this case, and it is 2.8 times 10 to the minus 2 reciprocal seconds. We want to know how long is it going to take, so we're looking for time, and we're going from 0.88 molar, which would be our initial concentration, and we're going to end up with 0.14 molar, which would be our final concentration. Remember, it's a reactant, so it's decreasing with time, as we would expect. So we would want to use, obviously, our first order rate law there. And by the way, even though it told us it was first order, if it didn't, we would know that by looking at these units here, and that would tell us it is first order, and it would be the natural log of A. It's equal to the natural log of A naught minus KT. And basically just plug and chug into here. So now the natural log of 0.14 is equal to the natural log of 0.88 minus the rate constant, which was given to us, and RT. I personally move it over. So I personally do a little natural log of 0.14, hit equals. Then I'm going to subtract the natural log of 0.88 from it, basically subtracting this to the other side. You do that, you get something like minus 1.838279485. Don't feel like rounding. Minus 2.8 times 10 to the minus 2 reciprocal seconds. Obviously, we're going to divide that to the other side. Also remembering that there is a negative sign there as well. And if we do that, we end up with a time that is about 66 seconds. The units of seconds really do come from here when we do that. Any questions on that there? So again, key to understanding the units there so that you can sort of apply the correct sort of formula when you're solving these are really critical. So half-life, as I kind of jumped a little ahead of it, again, is basically specific here for first order is that the half-life is the natural log of 2 divided by K. And again, if you do the natural log of 2, you will sometimes see that 0.693 number. That is what you get when you take the natural log of 2. So obviously, if we had a problem like this, what is the half-life of N2O5? If it decomposes with a rate constant of 5.7 times 10 to the minus 4. In this case, we basically would just plug it into our half-life equation. And if we do that, and I'll grab my pen here. So again, our half-life here, natural log of 2 over k, which means the natural log of 2 divided by our 5.7 times 10 to the minus 4 reciprocal seconds. Doing that little division there ends up getting us about 1200 seconds, give or take. You basically get 1216 seconds. Seconds comes to the top. Sig fig wise, 2 sig figs there rounds to about 1200 seconds, which is approximately about 20 minutes, give or take, depending on what unit of time you're looking for in this particular case. Any questions on that there? How do we know it is first order? So much like what we talked about in the previous problem, it is those units right there. Yeah. So it's those units associated with the rate constant, basically 1 over seconds, which indicates that it should be first order. Any questions on any of that there?
Yeah, I had a quick question. Is that a divide sign, or is that an equal sign between the ln2 over k and then the ln2 over the 5.7? Yeah.
Right here?
Yeah. Like between those two. Is that just an equal sign because we're like putting the k in for the equation following it?
Yeah, so it's the natural log of 2 over k, and basically that equals basically natural log of 2 over the actual number. Is that what you're asking?
Yeah, that's what I was asking. Yeah.
Yeah, I just made, they're basically equal each other. I just actually put the number in over here, and
Okay.
then that gets to here. Yep. Other questions? Okay. So obviously we talked about half-life when we did nuclear chemistry, but just a reminder, basically half-life really is the time it takes for half of whatever you started with really to kind of go away. So, about 10 half-lives or so, it's probably pretty much gone. So obviously if you started with, say, 10 circles at time 0, after your first half-life, you'd be down to 5 circles. After your second one, you'd be down to 2.5, and then after that, you need a calculator. But every half-life, obviously, you'd basically be dropping half of what you had previously to it. In terms of a first-order reaction, what we see is that the half-life is not dependent on the initial concentration. So it's actually just dependent on really the rate of the reaction, and there's no dependency on sort of kind of your initial concentration, which we'll see some dependence on half-life and concentration with 0 and second order type reactions. All right, so let's try another one here. We got this reaction going. It's got a rate constant. We actually, in this case, want to find what the concentration of our reactant would be after about 865 seconds have gone by, and we started with an initial concentration of 0.0225. So take a few moments here to see what you come up with. It was first order, but we could really determine that from the units that we see with the rate constant, which obviously means we have a rate constant of 2.9 times 10 to the minus 4 reciprocal seconds. Again, those units telling us it's first order. We're looking for really kind of the final concentration of this guy. We already know 865 is going to be our time, and we know the initial concentration here, 0.0225 molar. So obviously, again, we will use our first order equation here. We'll plug in what we got, and in this case, we are looking for A. We have our initial, which was 0. I missed a 0 there. 0, just 1, 2, 2, 5, minus our K, which is 2.9 times 10 to the minus 4 reciprocal seconds. And we do have the time given to us, 865. Let me just take a moment to also remind you of a very common mistake that people do make when they do these type of problems, and it does involve these two values and the units. In this particular case, we are okay. They're both in seconds, but it's very common in kinetics problems that the unit of time and maybe the unit of the rate constant are actually different time units. So that's also times something that people kind of screw up on. So just always take a quick look and make sure, again, in terms of the time aspect, that they are in the same units. Otherwise, again, you do need to do some type of conversion. Otherwise, your answer will be sort of off. If I'm not mistaken, I pretty much can clean up the right-hand side there. So let me do that. So we're going to take the natural log of 0.0225. We're going to subtract it from 2.9 to the minus 4 times 865. And if I'm not mistaken, we will end up with something like minus 4.0451. We now need to get rid of our natural log. To get rid of that, we basically take the inverse of the natural log, which is basically that E number, yes? Or that E value, I guess is the way to put that. So we're going to take E basically on both sides. When we do it on this side, it pretty much just kind of gets rid of that, and we end up with basically the concentration. We obviously want to do that and not forget, again, the negative part of it. And it looks like maybe we end up with 0.0175. Remember that this is a molarity or a concentration, so you do need the units of molarity here. And it really does come from this number, which has molarity in it, by the way. And technically speaking, this guy and this guy divide out, and the molarity sort of come back. Any questions on that calculation? Does it make sense? It does, because we started with obviously a higher number than we ended with. So clearly, if you did a calculation, you ended up with a higher number than you started with, you probably screwed up somewhere there, because that should not be happening. Any questions on that? All right, one last one here on first order. What is the half-life of this reaction? So see what you come up with. All right, so since we're looking for half-life, we want to think about our half-life equation, which again is specific for first order, which is our natural log of 2 over k. Again, does not mention, does mention first order, but again, if it didn't, we'd know it is because of that. We pretty much got everything we need. Temperatures, just a nice little number there, I suppose, not really necessary. So that's going to get our natural log of 2, which is our 0.693 number, divided by our 0.271 reciprocal seconds. Looks like we end up with 2.56 seconds. Seconds come to the top when we divide. That is a very, very quick half-life. That means basically every 2.5 seconds, whatever we started with is gone. Yeah, it's very, very fast. Any questions on that? Questions on first order reactions? Okay. So then let's talk about another very common order reaction, which is second order. And in a second order reaction, a couple of things are similar and maybe a little bit different than kind of first order. First off, there's really a couple of ways you could sort of get to write a second order reaction. You could have, like we see here at the top, one reactant that has an order of 2. You also could have, obviously, 2 reactants where each one has an order of 1. Potentially, you could have 3 reactants where each one has 1 and one has an order of 0. And here in a second order, it would probably either be that 2 combinations, 2 reactants at orders of 1 each, or 1 reactant of an order of 2 is most common. Again, if you think about sort of these orders, first order, second order, 0 order, why don't we talk about say third order, fourth order, and all those type of things? What we're really looking at in these things it's kind of like, how many reactants are sort of participating. So if you think about most chemical reactions that you come across, most of the time it's like 2 reactants, right? Or maybe 3 at the most. In those cases, we usually don't do reactions where we dump a ton of reactants in all at once. And again, so that's why, when we talk about sort of the different orders of reactions, first order, zero order, second order, those are the very common ones that come about, really based on kind of 1 or 2 reactants really participating. So that's sort of, why we have those type of ones here. We can do the same thing with our rate law here, which would be for a second order reaction here. And we can rearrange it and really solve for K. And when we do so, we get our typical units associated with a second order reaction, and that is 1/molar seconds, right? So much like what we saw there with our first order reaction, where if we see a rate constant has units of 1/seconds, we know it's first order. If we see one that has units of 1/molar seconds, it means that it is a second order reaction. Kind of very much like the first order as well. The seconds part of this does not always have to be seconds. It really is some unit of time. Again, seconds being really the most common unit that's used. But, if you had 1/molar minutes or 1/molar hours, that's still a sort of second order type of situation that's happening. Now, with a second order situation here, we could write really our rate expression, do a little rearranging, and we come up with a concentration time-dependent equation, our integrated rate law for second order, and it is 1/A is equal to 1/A naught plus a KT. These are our same sort of guys as before. That's, again, you can think of it as your final concentration. You can think of this as your initial concentration. Our K is still our rate constant. And again, our T here is still our time. We also, much like the other one, need to be cautious of units there and making sure that they are the same as well. Now, if you ever can't remember a half-life equation and you're good at math, you can substitute into the equation above the initial divided by 2, which is basically what the half-life is for A. Do a little solving, and when you do, you come up with the half-life equation here for a second order reaction. It is the half-life is 1/K times the concentration, or the initial concentration. So unlike first order, second order's half-life is actually dependent on your initial concentration. So the initial concentration does have an effect on really the half-life of this particular reaction. Now, also something different with this is the graph that we associate with a second order reaction, which is this graph right here. Taking our rate law and rearranging it just a little bit, we get 1/A is equal to KT plus 1/A naught. And this means that this is written in the form of a straight line. Y is equal to mx plus b. That means, as you can see on the graph on the bottom right there, on the y is 1/A. On the x there is our t. Different than our first order, where we had a negative sloping line. Here we actually get a positive sloping line. So this one will give us a positive sloping line. And because of that positive sloping line, that means that if you take the slope of it, it actually does equal K here, not negative K like it does on the negative sloping line. So much like first order, these are sort of the 4 things or so that you do need to know for a second order. Again, the units associated with K, the specific concentration time integrated equation there that goes for second order, the half-life equation, and again, the typical graph here that we have going on for our second order reaction. And as you can see, a positive slope happening here. Any questions on that there? All right, the last type of sort of reaction that we kind of deal with, and like I said, it really is based on the idea of, in typical reactions, how many are reactants are actually reaction. reacting. I'll spit that out right, I think. And that is a zero order reaction. And in a zero order reaction, you basically get it when your order, right, of your reactant is equal to zero. And if you do that and put that into the rate law here, we basically got that the rate is equal to the rate constant, which means that the units that we associate with K for a zero order are really the same units that we associate with rates, which is molarity over seconds here. So again, you can see the three sort of distinct reactions that we talked about: first order, zero, and second order. Each of them have different units associated with the value of K. And that, again, is an important thing to understand and know what those units are, so that when they don't tell you, you can sort of do the math correctly and go, oh, those units are associated with zero order. I should use the zero order equations. Or those are associated with first order, I should use first, or second order, I should use second order. Doing our rate expression, which is basically the change of concentration A over change of time equals K, gets us, again, sort of this integrated rate law. This is for zero order. It's almost identical to first order, except no natural logs. So no natural logs happening here. But again, that is basically our final concentration is equal to our initial concentration minus KT. Putting in the initial divided by 2 for A and doing some solving for T gets us our half-life here, where the initial concentration divided by 2K is equal to the half-life here. So here, the initial concentration plays a role as well in terms of the half-life. And that's exactly what we see with second order, but again, we don't see that with our first order. Much like the other two, we could do some good rearranging of that equation, and we end up with something that kind of, again, looks like our first order without the natural logs. And again, that is written in the form of y equals mx plus b. That means that the typical plot that we associate with a zero order is on the y, the concentration, and on the x is our time. And we see that again here, because this will yield us a negative slope. The slope of that line equals minus k. Again, not positive k, but again, that will then get us a positive rate constant value from that. So just like the other ones, those are, again, the important things to remember. Units associated with zero order K, our equation, our half-life equation, and then obviously our graph here. Now, one note about that graph, as I mentioned earlier, that graph may look familiar to you in terms of what is being graphed, which is the A versus time. Now, if you remember, we saw that with first order, this graph, but it did not result in a straight line. It resulted in this sort of decreasing line, very badly drawn there. So again, if you don't get a linear line with this graph and it looks more like this, decreasing with time, that again is first order. This down here is zero order, which definitely should yield you that straight line versus that sort of decreasing with time line. So again, like I said before, with first order, most of the time we look at the natural log of A versus time, and that gives us that straight line sort of relationship. But again, if you do see a concentration versus time where we have decreasing concentration over time and this sort of decreasing with time line here, it will be first order and not zero order, because if it's zero order, it should yield you that pretty straight line. Any questions on that there? So I want you to take a second here and see what you come up with. We got a second order. We're looking for what is the rate constant here. So take a couple minutes. The rate constant. So obviously we would not be able to determine that without that piece of information. So what it does tell us that we should be using our second order formula here, which is this guy. Again, remember this is plus, not minus KT. We have a couple things. We got our initial concentration, that is 0.01 initial. We have our time, which is like 500 seconds. We also have our final concentration of 0.001. So that's pretty much everything we need. So we'll plug those into the right spots there. So that's going to be 1 over 0.001 is equal to 1 over 0.010, too many zeros, plus K, and again, 500 seconds in this case. I personally will take 1 over the 0.001 and then subtract that to the other side. And if I do that, I end up with 1 divided by 0.0010 minus 1 divided by 0.010 gives me a 900, maybe somewhere here. There we go. 900 on this side equals K to the 500 seconds. And at this point, basically, we're going to divide that to the other side, divided by 500. Gives us a K value that is 1.81 over molar seconds is the units, because again, this is basically molarity on the bottom, which means this is 1 over molar here. And when we divide the seconds ends up on the bottom as well. And again, those are the typical units that we associate with a second order rate constant. Any questions on that calculation? All right, any questions on anything we talked about today? Probably a good place, I guess, to lay it up.